Alright, sorry. This is a little bit late getting going there. I was finishing an email off. Okay, so I'm going to put up a note on my screen here. Just to let you know what it is that I'm about to talk about. So today is Thursday, April 16th. So sooner than later is this the time to start thinking about Project 3, and then we'll do Lab 11 together. Okay, so let me bring up a browser and let's go look at Project 3 real quick. Somewhere, where's Project? Okay, there it is, it's hiding. Project 3. So that's coming up quicker than it seems. So the first thing I'll tell you is that unlike, well, all of the labs all semester have been giving you tools and techniques to solve the projects, but projects 3 and 4, the labs are heavily weighted toward giving you the building blocks of the project. So as you're completing the labs each week, you are getting a fair amount of the building blocks for the project. Number 3 and number 4 will be the same thing. So just so you know, you kind of have already been working on it if you've been doing the labs since Lab 10. So Lab 10 and 11. But let's go look at it particularly. It's going to look intimidating at first. But you already have a lot of the skills you need to begin working on it. And then where you're acquiring more of them as we do the labs. So what this project does, it accepts a single command line argument, which is meant to be the name of an input file, and then handle that argument. You've done this before, so you already have code that detects whether or not a command line argument was supplied, and if not, it prints an error. If the command line argument was supplied as a file name, but the file doesn't exist, or for whatever reason you fail to open it, you know how to code for that. And then finally, you know how to write code to open and read each line of the file into a vector. So you already have all those things, and you're going to continue doing that for the third project. So there's a difference in terms of what the input looks like, and some of you will just sort of quickly get what you're supposed to do here, but I know from experience that some of you are going to try to do you're going to want to just kind of repeat the same things that you've been doing over and over again, even in places where you shouldn't do that. So where you should repeat what you've been doing over and over again is handle the command line argument, open or fail to open a file, read its contents into a vector. That's the same stuff. But if you look at the file, and there's a link down here for a sample input file, it's very different. It does have a comment capability, so your code should handle comments. In my input files, the comments will always be the hash symbol. You probably should handle blank lines, even though I don't typically use them, but your code should probably ignore blank lines and ignore comments. But if you look at the nature of the data, this is not the kind of data that you're going to load a struct. So some of you are going to immediately copy and paste a struct in, like, how do I load the struct with the population? That's not how this one works. These letters are commands. So what you're supposed to do is you look at the first character of a line, and the first character tells you what your program is supposed to do. So the F means your program is supposed to do something. So the way I would set it up is either with the switch or an if-else statement that says if the command character, and they're all single character, if the command character is an F, then this thing happens. If the command character is a C, then this other thing happens. Some of the commands have data attached to them. So what's going to happen is some of these commands are going to tell you to add data to a linked list. This F probably means push front. So the commands that have you do something with data means that you also have to parse the data out of the command, and then you use that data to put it in a node. So these are all things to think about in terms of the third project. You know how to open a file. You know how to get its contents into a vector, and there's no reason why you can't begin to work out your processing code to look for specific commands and cause your program to react to them. You don't have to have the full behavior. You can just put an output statement. So if the command is F, then your program for now can just say, my program someday will do whatever F means with the 25. And else if the command is A, see out, my program will do whatever A means at some point in the future. So these are ways that you can get started on that project. The operations themselves, so the way this works is you're going to get, I have a whole bunch of these different files, so your program just sort of has to process an unknown set of commands. So your code has to be correct because you don't know exactly what combination of commands or how many you're going to get. The other things you look at, though, are the operations. So the operations file tells you what the commands mean. So if your input file line has a C as its first character, then your code is supposed to create a dynamic list instance. Dynamic, by the way, means do something with new. If the command is an F, then you should also have a number that goes with that, and you will push front that number. So that's the operations part. The outputs part tells you for each operation what your program should spit out. So for example, if the command is C and the operation is create instance, then your code prints out list created. You can see that, by the way, because my sample output file is the outputs that my code produced on the sample input file. So this takes some thought, meaning don't wait too long to sort of dig into it a little bit and think about what it is that's being asked, what it is that your code might do. The parts where you have to actually put data in a data structure and get it back out, that can be added in later. Okay, so the file processing part you can do, that's actually most of the code for this project is just the file processing. And there's no reason why you can't do that part even if you don't have the data structure underlying it. Okay, so the other thing, and I'm going to give you a hint about this, you need a doubly linked list. And I'm going to show you, and then I'll come back to this on Tuesday. What does it mean to be a doubly linked list? So let me do another code file. So a singly linked list looks like this. Public will have some stuff. The private section is the important part. So in a singly linked list, a singly linked list manages nodes that look like this. I'll put that first. Some piece of data goes in the node. So these are what the singly linked list manages is nodes. For a singly linked list, each node contains a value and then a link to the next node down the chain. And then the singly linked list keeps track of the first node in that chain, which it refers to as the head of the list. Okay, so a doubly linked list. And then, of course, all the functions that it uses to do that management work. It also manages a node. I'll come back and get that later. That stores some value. Now, the difference here is that a doubly linked list has links going in two directions. It keeps track of the next one after it, but also the next one in front of it, which allows us in applications to sort of iterate backwards and forwards through the list and do some other things that are easier to do when you can move both directions in the chain. So I'm just sort of introducing you quickly to what the doubly linked list has that's different. Its nodes are different. They have things going in both directions. I'll draw a picture in a second. In fact, I'll draw a picture now. So here's a node in a doubly linked list. Previous, next, and then it contains the value inside of it. So if you have a bunch of them, the chain's going to be connected in both directions everywhere. That's project 3 challenge, is to make these algorithms work with the links going in both directions. Now in terms of the list itself, it still has a head. But it also now has a tail. So that your algorithms can actually start at either end and work in either direction. So I'm just sort of, that's the concept that you're exploring when you implement this data structure for the third project. In the labs, we're doing singly linked lists, which is this thing. The algorithms are very similar, except for the singly linked list only has to worry about the chain going in one direction, whereas the doubly linked list has to do the extra work of maintaining the chain in both directions. Okay, so let me hide some stuff so we can go on to the lab. I'll come back to that, but that also hopefully is a cue for you to ask some questions as we work over the next few weeks. Most of the algorithms will be developed in the singly linked list labs, but you then have to extend them so that they work with the doubly linked list instead. So you'll sort of copy the functions and then update them and extend them so that they work as a doubly linked list as opposed to a singly linked list. Okay, so now I'm coming back to Lab 11. Lab 11, all it really does is add 3 functions. So it keeps the constructor, which doesn't change. It nulls out the head pointer because at the start the list is managing no nodes, so there's no head or first node to keep track of. The size should be 0 because there's no nodes. It hasn't counted any because it's not managing any yet. Still has push front, which is the ability to tack something on to the front of the list. Still has the front function, which retrieves the value from the front of the list. Still has the size function, still has the check for empty, which is just useful. Is the list empty? In other words, does it have any nodes in it? For me, I just use the size of the list to tell me whether or not it's empty. This just is a convenience function to be able to say is if the list is empty, do something. And it still has toString. That doesn't change either. So those functions, I just pulled them from Lab 10 and I plopped them back in here. Okay, so I'm just going to work my way from top to bottom. So the destructor, which I went over on Tuesday, so if you didn't watch that, weren't there, or didn't watch the video, there's a video for Tuesday, April 14th, where I talked about destructors and what and when they happen. But the destructor just says invokes clear. So if I look down here, there's a clear function. It's empty, I haven't implemented it yet, but that's really all I'm supposed to do with the destructor is make sure that the nodes are cleared out. If you saw Tuesday's class, that's deleting all the nodes. It's freeing up all that memory that was taken with new. So the clear function is going to do the other end of all those new nodes and delete all the nodes. But for the destructor, it can just use that function to do the job, and the function will do it. So that's all it has to do. Just clear out all the nodes as the list is being destroyed. Destroy all the nodes that it was managing. That's all that does. Okay, we did pop front, but I'm going to do it again. Just because I think it could be helpful to repeat. So I'm not going to draw a picture. Well, I will draw a picture of this because I want to encourage you to try it. I don't like the angle that I'm getting here. Okay. So the whole idea of pop front is to remove a node from the front of the list. But if there are no nodes on the front of the list, there's nothing to pop, to remove. So I need to write code to handle that situation so my program doesn't crash. So if the list is empty, there's me using that convenience function. If the list is empty, I can't pop. So I will throw instead this logic error that it tells me to throw. That's a deal breaker. You can't pop a node off of an empty list. That probably makes sense. Okay, otherwise though, what I'm supposed to do is remove the first node, leaving the next node as the new first node. So I not only have to delete this node, but I also need to move this marker, this head pointer, over to the next node over, because that's the new head of the list. If I pop the front one off, this one's going to be the new head of the list. So I have to do that work. So the way I do it is I grab myself an additional pointer. So I'm just going to make myself a pointer t, so node star t. And then with pointers, the way I like to understand the assignment operator is t points at what? I want it to point at the same thing that the list head is pointing at right now. So t points at the same thing that head points at. So after that line of code, this is what I have. I have head pointing to the node. This is the one who's doomed. I'm going to delete it. And I have t pointing to this node. And this is just, it's a good habit to be in because it is a good way to prevent bugs where you accidentally break something. Anyway, so I just grab myself this extra pointer. I'll call it T for temporary, and point it at the same place that head points at. All right, now that I have that, I can move head over to the next one over. So in code, I'd say this head equals, but what that really means is the head pointer now points at something else. The thing I want it to point at is this next one over here. Well, the next one over here is currently the next one from head. So if I take the current head and if I grab its next one, then saying this head points at the next one is really just saying shift this over so that it points at the next one over. So that's what this head equals. This head next shifts head over. So I still have T pointing here. I didn't move that. And now I have head pointing here. But now that I've moved head over, I can use T to destroy the old one that I wanted to destroy. So I'm going to do that. So I delete it. So it's now gone. And then I'm also going to back off the size by 1 because I just removed a node. So everything about that node is now gone. Because I declared T, just sort of this temporary, I didn't do a new node or anything like that. I just said point T at an already existing node, which was head. Once the function returns, the node star T, because it was declared inside the function, just goes away. And what I'm left with is head pointing now at a different node as the first one because the old one went away. That's pop front. And I'm just going to work through all of them now because I'm feeling confident. So clearing a list is the same thing. I don't know why I drew it there. I'm already unhappy with that picture. Clearing the list is similar to printing it, except we're deleting stuff as we go. So I'm going to show you sort of the manual way to do this, and then I'll show you the much easier way to do this. So we'll do it manually first, and then if it hadn't occurred to you, if it is occurring to you, there's an easier way than what I'm doing. Hopefully what I do as my second stab at this will be what you were thinking. So clearing a list means deleting all the nodes. So I have to work my way down through the nodes, deleting them all. So I'm going to use a similar approach. I'm going to grab a T pointer and point it at the same thing that head points at. And then I'm going to say while T is not null. So null is the value that I use to detect whether at what point I've fallen off the end. So if this T manages to walk all the way down here and then be sitting on null, I know I'm done. So I'm using that kind of as my indicator that I must be at the end. Because T, if I march it along, will eventually become null. Okay. So I'm going to do it wrong first and just show you in the picture how I would know that I did it wrong. So I'm going to do this. That's what I really want to do is delete T's and then move the head over to the next one and then have the T follow. So I'm going to delete nodes and then I'm going to move head over and then I'm going to have T follow it, which is what those lines do. Delete one, move the head over. So the order that I have it now is I delete T. Now if I'm drawing a picture of this, I will immediately recognize, well, if I delete the node that's underneath head, there's nowhere to go next from. That's a problem. I can't get the head moved over there because there's no place to move over from. So I can't do the delete first. So let's try doing the delete second and see what happens. All right, so let's clean up let's make a new picture. Okay, so what if I put off deleting the T until after I moved head? Well, let's try it. So now the first thing that I do is I move the head over. That seems all right. I delete T. That seems all right. And then I say point T where head is. That also seems all right. That's pretty good. Now my loop catches and I say, is T null? No, it's not. So I'm going to move head over. I'm going to delete T. And then I'm going to have T follow head. That's still okay. Now my loop catches. So head next, which now means that head's sitting here on null, which means it ran off the end. So far okay though. T gets deleted. And then T follows head, which means that now T is also pointing at null. Now the loop catches and T is null, so the loop stops and we have cleared out the list. One thing that we're not doing is backing off the size every time we delete one, which we should do. That's the clear algorithm. But now I'm going to write a version of it where I just use my own dang functions. So I recognize that I already have a function that removes one node at a time, which is pop front. So I could actually clear the list if I just repeatedly pop the front. So if I can figure out some condition to use to tell me how long I can keep popping the front, that would solve my whole problem a lot more simply. And I have a function for that as well. I can say, while the list is not empty, pop the first one. Pop the first one, pop the first one, pop the first one. So as long as it's not showing as empty, it'll just keep popping the first one. And if I do that long enough, then it will become empty and all the nodes will have been popped off. So this is an alternative, and I think it's a lot easier to read this way. While this list is not empty, pop the first one. And just keep popping the first one until the list is in fact empty. Both of those techniques works. The first technique is harder to figure out as an algorithm. The second one is easier to read and understand. While this list is not empty, pop the front node. And it handles the rest of the job for me. At least I'm going to run a unit test and find out. But try to keep that in mind. I've tried to sort of draw your attention to that, but if you're not in the habit yet, just always ask yourself, do I already have a function that somehow I can leverage to solve this problem? Because if I do, I can save myself work. I think that this is a pretty way to do this. While the list is not empty, pop the front node. And it'll just keep doing that until the list becomes empty. There's even a protection here in pop front so that if I accidentally try to pop it beyond the point that it already became empty, it handles that too. So pop front actually handles me making mistakes elsewhere in my own code. Okay, let's try out the unit test and see where we're at. Do I have a catch in here? I do not. I'll remind you. Let me see. Can you see? No. I'll remind you as I'm doing this that the compiler needs to compile the CPP stuff. So I worked on slist.cpp, but my program is also uh, implemented in lab11.cpp. I am not compiling catch.hpp. I am not compiling slist.h. You don't compile .h files. You don't compile .hpp files. Even in your makefile, when you write a compiler command, it doesn't change. A makefile is just a place to store compiler commands, so that part doesn't change. I'm going to call it lab11.exe just because sometimes I go through and delete these compiled things. Oh, I went back to this old style, didn't I? slist.h, that means since I called it slist.h with little s and l, when I stored it in code, the reference needs to be the same. So that's lab 11, line 7. So I'll just fix that real quick. Yeah, so it doesn't match the way that I saved the file on my computer, so I'll just change it in code to match. Okay, so I'm passing them all in the first shot, which pleases me a lot. I'm going to try it one more time with my less elegant clear algorithm and see if it works just the same. It should. Yeah, still passes, so that's good news. Did I touch everything? I think I did. The destructor, pop front, clear, and we looked at 2 different ways to do it. It's up to you. As long as it works, that's the important part. I just think that the shorter version is prettier. I like this one better for my own purposes. So this code is meant to give you some hints about how you would do a doubly linked list. I'll give you one more hint, and then I'll kind of shut up for the day because this was a short lab. Let's look at this constructor, and let's alter. Let's do one for dlist. So just right here, I'll just do it. So what would the constructor look like? Oh, there's also a size and nodes. So in the singly linked list, I nulled out the head pointer and I set the size to 0. So that would be the same, that part, size to 0, head to null. But because it's a doubly linked list, I can also come from the other end of the list, which means that I have a tail that needs to be nulled. I don't need to save that. The other thing I could do if I wanted is I could, and I recommend it, see if I can sort of steal the node constructor from list. And I know what the node constructor did because I have slist.h in here. Alright, here's the node constructor for list. Sets next to null value to new value. So here's the node stuff. Not that, this part. So next to null. But now I also have a previous, so I would null that on a new node and then set the value to the given value. So again, this is just sort of hints about your challenge in project 3 is to take the ideas from singly linked list and adapt them and extend them into a doubly linked list, which is a fancier data structure. Um, but the starting point is just realizing that a doubly linked list, it manages a slightly different kind of node, which is a node with double links, as opposed to a single link, double links. That changes the way the nodes are constructed, because you want to null out both the links to start. It also changes the way the list works. And pictures can super duper help. So if you're not in the habit of drawing pictures, you should. It takes practice to draw pictures and make them work for you. And the only way to get that practice, of course, is to do that practice. So highly recommended. Helps a lot. Whenever I have visited people working at places like Amazon or Google, whatever, they always have whiteboards and they draw pictures of this stuff too, because it's just way easier to get the picture in your head as an actual picture as opposed to trying to translate code into a picture. Okay, that's it for me for this week's stuff. I'll sit here for a few minutes and give you a chance to ask questions if you have any. Thank you. You're welcome. Yeah, there is a Discord. Um, I can put that. Well, if I put the link in chat here, other people send me an email and I'll send you the. Please send me an email for the Discord link. I've. It will only allow like 24 people. It's our number of people to join it, so I don't want to put it on the chat and have strangers use up your seat in the Discord. Which I know I could change. But anyway, send me an email if you still need the Discord link, and I will send it to you. But yeah, there is a Discord, and several people have been in it for a while, although we don't get a whole lot of chat in it. Thanks. You too. Have a good weekend, everybody. I'm available by email. But otherwise, I'll see you at 11 on Tuesday next week.